So with one wire, we can communicate one bit of information. We could say, turn a pump on or off. If we use two wires in tandem, we can communicate two bits of information. But take a look at how much more information that is. How many different combinations of highs and lows can we get with two wires? We can get 4 different combinations. Both wires could be low, or both wires could be high, or one or the other could be high while the other is low. If we add a third wire, how many different combinations can we get? We can now get 8 different combinations. Let's chart it out. If we have 4 wires, how many combinations can we get? 16. Let's chart it out. So as you can see, we double the number of combinations we have available with each wire we add. So we can actually develop a system to communicate large numbers using multiple wires, like this. The first wire represents 1. The second represents 2. The third represents 4. The fourth represents 8. By the way, one of these wires represents a bit. 4 wires represents a nibble. 8 wires represents a byte, spelled with a Y, not an I. No, I'm not making this up. If we have a bank of wires like this together to communicate digital information, we call this a bus. So a bus in digital is simply parallel wires which communicate a digital signal. So if we have a byte of information transmitted over an 8-wire bus, the wires each represent 1, 2, 4, 8, 16, 32, 64, and 128. We call this the least significant bit because it's the small end of the scale, and this one the most significant bit as it's the high end of the scale. Now binary can be written either way, with the least significant bit to the right or on the left. Conventionally, if we write a decimal number like 312, what's the least significant number? 2, which is on the right-hand side. So it would be confusing convention if we wrote the numbers backwards with the 2 on the left side. There's no law saying we can't, but we would have to indicate that the 2 was the least significant digit. So when dealing with binary, keep an eye open for that LSB or MSB annotation, which indicates which digit is the least significant or most significant bit. If it doesn't say, then we assume the least significant bit is to the right. Ooh, check this out. Get it? Ha! The number 10 is binary for 2. So either you understand binary and you get the joke, or you don't. Get it? Ha! Never mind. You guys have no sense of humor. But my geeky joke brings up a point. Now, if I wanted to communicate the number 0, all wires would have zeros. If I wanted to communicate the number 16, only the 4th wire representing 16 would be high. If I wanted to communicate the number 33, 2 wires would be high, 32 and 1. So you can see all I did was add up the numbers. Now if this wire, and this wire were high, what number would I be transmitting? If you guessed 98, you are correct. We simply add up the numbers represented by the highs on certain wires, in this case 2, 32, and 64. Add them up, you get 98. What if I wanted to communicate the number 255? Think about that a moment and see if you can figure it out. You've got 15 seconds. Okay, time's up. If you said all of the wires are high, you are correct. So with a single byte, how many numbers can we communicate? How many different combinations? If you said 255, you were close. It's actually 256. So what's the 256th combination? 0. all of the wires low. A 0 can be just as important as a number as any of the others, right? So this numbering system is called binary. Binary for 2 because our numbering system is a base 2. The normal numbers we use are called decimal. Decimal for 10 because we use 10 different numbers, 0 through 9. So we can transmit the number in binary over a bus of parallel wires. This is called parallel communication. Or we could do it like they did with the fax machines in the 1800s, which used a single wire to communicate huge numbers. If we take a single wire and the transmitter and receiver each have a clock so they can keep time, we can agree upon a communication system. The transmitter and receiver can establish the timing and say, we will communicate at 1 pulse per millisecond. So the receiver starts listening. 1 millisecond goes by and there is no signal, so it writes down a 0. This is the least significant bit. Another millisecond goes by and no signal, so it writes down a second 0. The next millisecond on the clock, it does get a high, so it writes down a 1. The next millisecond, the signal is low, so it writes down a 0. The next millisecond, the signal is high, so it writes down a 1. Then a 0, then a 1, then a 0. So we just communicated an 8-bit or 1 byte binary number using a single wire. The number was 00101010, which is 84. 4 plus 16 plus 64 equals 84. By setting up a timing cycle, we were able to communicate a series of numbers over a single wire. When we communicate a series of numbers like that, it is called serial communication. So parallel uses multiple wires in parallel to communicate the information, but serial uses a single wire to communicate a stream of information. Notice also that we are only dealing with numbers. Now, really, that's all computers do, is deal with numbers. The fancy pixels on your computer screen showing this ugly mugshot is nothing but a whole lot of numbers being tossed around from a computer on the internet to your computer, which is taking those numbers and processing them to different colored lights on and off on your computer screen. It's all numbers. But yet we humans use way more than numbers. What about our entire alphabet? Samuel Morse established rules, a communication chart, which became the standard for communicating with dots and dashes over the telegraph wires. In like fashion, back in the 60s, with the advent of the first computers and computer systems, the American Standards Association set out to establish a chart for communicating with ones and zeros. This became known as ASCII, which is an acronym for American Standard Code for Information Interchange. Basically, they established that certain binary numbers could represent certain characters. With a single byte, they could transmit 256 different characters. That's more than enough to transmit the numbers 0 through 9 and all of our characters of our alphabet and punctuation. You could designate several numbers to represent things like control characters. Now, back in the old days of typewriters, you had a carriage return. That was where you reached the end of the page for the line. You pulled on this big arm, which scrolled the paper up one line and brought the paper back to the left side of the page. On modern computers, the return key is the equivalent of this function. So one of the characters could be a return signal. It wouldn't print on the screen. It would tell the computer to start a new line. So here's the ASCII chart, and you can download this in the downloads section. Just ignore the hex figures. We'll explain what those are in the next lesson. Now, while this standard has been replaced with a new chart called UTF-8, the ASCII character set still works in the UTF-8 system. We're going to be using some digital systems that operate on the ASCII character set. For instance, in your kits, you will find the digital LCD display. When we get it up and running, we will tell the display what to display by sending it ASCII codes. So notice that the chart starts with control commands like start of heading, horizontal tab, escape, etc. Starting at 33, we have the first punctuation mark, an exclamation mark, through to 48, which starts the numbers and math symbols. Then the alphabet in upper and lower case, and some special characters. In the upper end ASCII table, we see a whole mess of special characters and stuff, and in the next lesson, we'll explain why there's an upper half of the chart.